In this video, we are going to learn about Newton's laws. This is the most important topic in whole of physics. Before we start discussion on Newton's laws, let me tell you two situations where you cannot apply Newton's laws. First situation, when the speed of objects is an appreciable fraction of the speed of light, we have to apply Einstein's special theory of relativity. Second situation, when the size of objects is on the scale of atomic structure, then we have to apply quantum mechanics. There is a very big universe in between these two limits, and there Newton's laws are applicable. Earlier, people used to feel that every body has an inherent tendency to come to rest. They felt that a body at rest will remain at rest forever, but a moving body wants to come to rest. This wrong concept was corrected by Galileo, who said that a body at rest will remain at rest forever unless some external unbalanced force acts on it. And a moving body will continue moving with uniform motion unless some external unbalanced force acts on it. This formed the basis of Newton's first law. So now let us learn Newton's first law. Let me state the law. Every body continues in a state of rest or state of uniform motion in a straight line unless it is compelled to change that state by an external unbalanced force. Every word in this law is important. First thing is that Newton's first law is applicable to every body. Some books you'll get in the market which will tell you that Newton's first law is applicable for inanimate objects. That is wrong. Newton's first law is applicable for everything, living things, non-living things. When I walk, what force makes me accelerate? No, not the food I have eaten, that energy coming from that is not making me accelerate. For acceleration, we need an external force, and we are able to walk because of friction. If friction is not there, you cannot walk. You cannot walk fast on the beach. You cannot walk on ice. All that is because friction is not there. Friction is the external force that helps us accelerate forward while walking. Which force makes a car accelerate? Again, friction. If friction is not there, car will not accelerate forward. If you take your car on an oily road, the wheels will rotate, but the car will not accelerate forward. On the beach, the car will not accelerate on a sandy road because there is no friction. So for acceleration, we need an external force, and that is true for every body, right? Second thing, if a body is at rest, it will remain at rest unless some external unbalanced force acts on it. This is called inertia of rest. The tendency of a body at rest to remain at rest unless acted upon by an external unbalanced force is called inertia of rest. So that is, a body at rest will remain at rest, right? You are sleeping, you want to continue sleeping unless somebody wakes you up. Now, inertia of motion, the tendency of a moving body to continue moving in a straight line with uniform motion unless it is acted upon by an external unbalanced force is called inertia of motion. If you are playing, you want to continue playing. So that is inertia of motion. Just an example to make you understand the concept. One important thing is that only an external unbalanced force can accelerate a body. Internal forces cannot accelerate a body. Now you may think, what is this unbalanced force? Balanced force means the sum of the forces is equal to null vector. All the forces add up to 0. Then they are balanced. A balanced force can deform a body. If I take a bottle, press it like that, it gets deformed. So balanced forces can deform a body. For accelerating a body, we need unbalanced forces. Unbalanced force means the net force is not equal to null vector, net force is not equal to 0, so body accelerates in the direction of the force. Now one very important question to think about is that why is the first law required? Newton's first law can be mathematically derived from Newton's second law. In fact, Newton's third law also can be mathematically derived from Newton's second law. Then why did Newton give 3 laws? Why do we have 3 laws? We'll discuss about this in detail as we go along, but first let's try to understand what is force. What is the meaning of force? A force is an interaction that can accelerate a body. Force and acceleration are related things. A force can cause acceleration. How many ways a body can accelerate? How many ways the body can change its velocity? Right? Velocity can change in magnitude, direction, or both. So there are 3 ways a body can accelerate. Velocity can change in magnitude or direction or both. Now, what is the SI unit of force? Newton. All of you know that. What is the CGS unit? Dyne. So let us try to find out what is 1 Newton by 1 dyne. What is the dimension of force? Don't remember? Start from velocity. Velocity is distance upon time. So LT minus 1 is the dimension of velocity. Divide once more by time. Then you get dimension of acceleration. LT minus 2. And what is force? Mass into acceleration. And that is what is Newton's second law. So dimension of acceleration is LT minus 2. Dimension of force will be MLT minus 2. Right? So 1 Newton by 1 dyne is equal to MLT minus 2 in SI divided by MLT minus 2 in CGS. What is the unit of mass in SI? kg. Unit of length? Meters. Time? Second. Unit of mass in CGS? Grams. Length? Centimeter. And time? Seconds. So now you see that second will get killed. And what is 1 kg? How many grams? 1000 grams. A more civilized way of saying that is 10 to the power 3 grams. 1 meter is how many centimeter? 100 centimeter. Okay, we can say that as 10 to the power 2 centimeters. And here we get gram centimeter. And what do we get here? 10 to the power 5. So therefore, 1 Newton is 10 to the power 5 dynes. Right. Now let us try to understand why we have Newton's first law. Newton's second law, we'll see a little bit later, is F equal to ma. This equation comes from Newton's second law. And if force is 0, acceleration will be 0, because if mass is not 0, then if force is 0, acceleration is 0. So that is what is Newton's first law. If there is no force, there is no acceleration. Then why do we have the first law? Newton could have stated the second law and mathematically said that if force is 0, acceleration is 0, and that becomes a part of second law. We don't need the first law. So why is the first law there? The answer to this question is Newton's first law defines an inertial frame of reference, and without defining an inertial frame of reference, we cannot state Newton's second law. Now, what is this inertial frame of reference? What is frame of reference? Frame of reference always refers to the observer. It refers to the perspective from which an observer views a situation. There is no standard frame of reference in the universe. There is no stationary platform from where we can observe all motion. All of us are living in a spaceship called Earth. Earth is rotating and going around the sun. At what speed does the Earth rotate at the equator? Every point on the equator is rotating at a speed of 1600 km per hour. You cannot imagine this speed. In 1 hour, a point on the equator moves by 1600 kilometers. Okay, here we cannot move at 10 km per hour on Indian roads. But the Earth is rotating at a speed of 1600 km per hour at the equator. At what speed is the Earth going around the sun? The Earth is going around the sun at a speed of 1 lakh km per hour. You cannot imagine this. In 1 hour, the Earth travels 1 lakh km. That's why it's able to complete one revolution around the sun in 365 days. Is the sun at rest? Or sun is moving? Sun is moving around the center of the Milky Way galaxy. At what speed? At a speed of 9 lakh km per hour. The sun, along with the entire solar system, is going around the center of the Milky Way galaxy at a speed of 9 lakh km per hour. And all the galaxies are moving with respect to each other. So in the universe, there is no stationary platform where you can stand and say, the perspective I am having is the correct perspective. Everything is moving. So for this, we need to define an inertial frame of reference. What is an inertial frame of reference? The other name for this is unaccelerated frame of reference. Inertial frame of reference is a frame of reference in which Newton's laws can be directly applied. What is the meaning of this? We said that without force we cannot have acceleration. But suppose you are standing in a bus and the bus suddenly starts. Then you fall backwards. The bus driver has not come and pushed you, right? So why do you fall backwards? There is no external force acting on you. Even then you fall backwards. This is because we are looking at you from an accelerated frame of reference. In an accelerated frame of reference, we cannot apply Newton's laws directly. In an inertial frame of reference, we can apply Newton's laws directly. Now, where do we get an inertial frame of reference? Where will we get something which does not have any acceleration, we are sure? We cannot find that. So Newton said that if you find one inertial frame of reference, then any other frame of reference that is either at rest with respect to this inertial frame of reference or moving with uniform velocity with respect to this inertial frame of reference will also be inertial. And in this inertial frame of reference, you can apply Newton's laws directly. Please remember, this frame of reference always refers to the observer. It has got nothing to do with the object. So inertial frame of reference is that the observer is having zero acceleration. Now one obvious question is this earth an inertial frame of reference? Can we apply Newton's laws directly on the earth? Answer is, earth is actually not an inertial frame of reference because earth rotates. We saw that high speed and earth goes around the sun and even at a much higher speed. So how can we apply Newton's laws to the earth? Remember, speed of the earth is huge, but acceleration is small. Because of rotation, every point on the equator has an acceleration of 0.034 meter per second square. This is negligible compared to g or whatever normal acceleration we face on earth. So in most cases, we can forget this acceleration. If we look at the acceleration the earth due to revolution around the sun, that is 1/6 of this. So it will be 0.006 meter per second square. So this is much lesser. So you can forget about this also in most situations. So remember, the earth is actually not an inertial frame of reference, but whatever day-to-day small problems that we encounter, the earth approximately behaves like an inertial frame of reference. And remember, frame of reference refers to observer. It has got nothing to do with object. Inertial frame of reference, you can directly apply Newton's laws. In an accelerated frame of reference or non-inertial frame of reference, we cannot apply Newton's laws directly. We have to bring in something called pseudo force, which we'll learn later.